All right, welcome to Unit 7, Inference for Quantitative Data with an emphasis on means. In this video, we are going to examine topic 7.7, justifying a claim about the difference of two means based on a confidence interval. So the big thing in this video is, the last part here about justifying a claim, but we're actually going to talk about a couple other things in this video that are important for you to remember when talking about a confidence interval. So first, and we've gone over this several times, but it's super important to understand, what does C% confident mean? So in a problem where you're finding a 95% confidence interval, what the heck does 95% confident mean? Or 99 or 90 or 92? What does that mean? Well, it's important that you understand this sentence. In repeated random sampling with the same sample size, approximately C% of confidence intervals created will capture the difference of population means. All right, let me do my best to explain this again. Remember that when you have this sampling distribution, we can't make it because we don't know the true difference that's in the middle. But the true difference is smack dab in the middle right there. We just don't know the true difference between the populations. So population 1 minus the mean of population 2. We don't know that, but we know that in this visualized sampling distribution, it's smack dab in the center. So the idea is that a sampling distribution represents all possible differences between sample means. So, there's many different differences, right? There's all kinds. There's differences that could be on this side. There's differences that can be on this side. But in the end, the mean of all those differences should be the true difference. Because naturally, some differences are going to be more and some differences are going to be less, but the true difference would just be smack dab in the center. So here's where the idea of confidence comes in. Remember, if I look at a sample from population 1 and I get a mean, and I look at another sample from population 2 and I get a mean from that sample, I'm going to have a difference, right? And somebody else can go and do this, right? So I could create a confidence interval based on a difference from my two samples. But maybe somebody else gets two other samples and gets a different interval. And then somebody else, and then somebody else, and then somebody else, and somebody else, and then somebody else. The idea is that, yes, we found one confidence interval based on our two samples. But, somebody else can go and get their own samples and find a completely different confidence interval. And the idea is that we're very confident of all those possible differences out there. We're very confident that ours is one of the ones that's in the middle. So if we're going to be 95% confident, we know that 95% of samples are right smack dab in the middle. In fact, this is telling me that so many sample differences are going to be in that middle range that I'm just betting mine's one of them. Therefore, my interval will capture the mean. So if my sample was, let's just say my sample was right here, when I build the interval, boom, I caught the truth. Or let's just say my sample was down here. When I made my interval, boom, I caught the truth. So the idea is that, yes, you're finding one confidence interval based on your data, but you have to be aware of the fact that there are many, many other confidence intervals out there created from other samples. And the idea is that of all those intervals out there, 95% of them will capture the truth because 95% of samples are supposed to be right smack dab in the middle. So that's what C% confidence means. This is really what it's all about here, guys. So please make sure you take the time to understand that. All right, let's move on and talk about the interpretation. Step 4 is a step that a lot of kids mess up. They do all this awesome work to get to there, and then they flounder through the interpretation. So please make sure your interpretation is very clear. An interpretation for a confidence interval for the difference of two population means should include a reference to the samples taken and details about the populations they represent. So you got to make sure somewhere in there you're saying, hey, I'm 95% confident, blah, 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 based on the samples I looked at, right? Because your information, your interval is only based on your samples. Somebody else could get a different interval, right? So you got to make sure you reference that. And you got to give those details about the population. And this is where I'm begging that you compare. Make sure your interpretation compares the two specific population means you're looking at. When we talk about comparing, we use words like more than, greater than, less than, smaller, bigger, above, lower. Don't just inform, compare. So let's look at two examples to make sure we understand this. In the previous topic, we actually calculated some intervals, and we did this one where we were looking at the mean number of books American teens read, versus the mean number that Canadian teens read. And our interval came back negative 0.02 to positive 1.02. I do a little bit of rounding there, but to 2 decimals, that's what we got. Now, when you interpret this, you got to make sure you compare. Now, I was specifically looking at Americans minus Canadians. So the negative would mean that the Canadians could potentially be more than the Americans, or the positive means that the Americans could be more than the Canadians. So I'm saying I'm 90% confident that the American teens read anywhere from 1.02 more books on average per year, because that's the positive. And if I subtract in this order, a positive means the Americans were more, but the negative means that the Americans could actually be 0.02 less books per year than the Canadian teens, based on the two samples examined. So it's very important that you understand that you need to compare, right? Use words like more or less. Don't just say the difference is in between here. That's just informing. You need to make sure that you're comparing to give a really nice answer about these two different population means that you're looking at. Another example we looked at was the diameters of oak trees in the northern states versus the southern states, and we did oak trees mean in the north minus oak trees mean in the south, the mean diameter. And we got an interval of 1.20 to 14.00. Once again, I did a little bit of rounding there. So remember, what this means is that they're both positive. If both positive, that means that I'm very confident that the north oak trees on average are bigger. So I'm 90% confident, based on the samples taken, that oak trees from the northern states have a mean diameter anywhere from 1.2 inches to 14 inches bigger than the oak trees in the south. So I'm pretty confident that on average, oak trees in the north are bigger, because my entire interval was positive. All right. And the only other thing I want to point out here was, remember, what you got to put this somewhere, right? Based on the two samples examined, based on the samples taken, right? You got to make sure that you're saying that, listen, my information is only coming from my samples. I'm not saying that this is true for every interval, because remember, every interval is going to be its own interval. So this is just based on what we looked at. So please make sure those interpretations are very clear and that they are comparing with context. All right, let's talk a little bit about the width of the interval. This is actually the fourth time we've talked about this idea, and this is super important that you understand. When all other things remain the same, the width of the confidence interval for the difference of two means tends to decrease as the sample size increases. Bigger samples vary less. So if you look at bigger samples from each population, you will get more accurate measures of those populations, hence a more accurate interval. So when sample sizes go up, intervals shrink, right? A very wide interval is awesome. Say, I know that it's anywhere from 2 to 40. Okay, great. That's a very wide interval. But it'd be much better if I said, hey, I know the answer is anywhere from 31 to 33. That's a nice, tight, small, accurate window. And the only way you could get that, again, all other things remain the same, is bigger sample sizes. All right, the final thing we're going to talk about in this video is being able to use a confidence interval for evidence. Now, the only thing I got to make sure here is that you read the question. That is the number one issue I have found with students. They don't read the question. They just blindly answer, yes, no, I don't know. They don't actually take the time to answer the question and give their answer based on that question. So a confidence interval for a difference of population means provide an interval of values that may provide sufficient evidence to support a particular claim in context. So again, take your time, read the question, and then properly answer with a yes or a no. Here's an example. All right, let's say that a 99% confidence interval that is estimating the difference between the mean number of minutes athletes spend on homework per night and non-athletes spend on homework per night at a large high school is found to be 2.87 comma 13.59. So before we read the next question in red here, let's make sure we understand that we were doing the mean number of minutes that athletes spend per night on homework minus the mean number of minutes that non-athletes spend on homework. Now, what I'm noticing right away is that my entire interval was positive, which means that the athletes are spending more time on their homework. All right, now let's go ahead and read this. It says, does this interval give evidence that the mean number of minutes athletes at this school spend on homework per night is higher than the mean amount of time non-athletes spend on homework per night? Yes, 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 right? It clearly says, does the interval give evidence that the mean time that athletes spend on homework is more than non-athletes? And because my entire interval was positive, showing that it's anywhere from 2.87 more minutes for athletes to 13.59 more minutes for athletes, I am very confident. I have a lot of evidence with this interval that athletes do spend more time on their homework. So obviously I just wrote down the answer yes, but make sure you explain as to why that is. It's the fact that the entire interval is positive. And that's telling me that the athletes, based on my interval, 99% confident, are going to spend more time on their homework. So this interval does give me evidence to conclude athletes spend more time per night on their homework than non-athletes. All right, here's the second example. A 95% confidence interval for the difference between the blood cholesterol levels measured in milligrams per deciliter of adult volunteers who take an aspirin every day and adult volunteers that don't take an aspirin every day is found to be negative 22.15, 2.47. All right, let's talk a little bit about this problem before we read the question in red. So first we're looking at the mean blood cholesterol levels of adults who take an aspirin every day minus the mean of adults who do not. So I'll put an N for not taking aspirin every day. So we're looking at the mean of adults who do take an aspirin minus the mean of adults who do not take an aspirin every day. So just to give you a little bit of a background on this problem, what we did was we took 100 volunteers and we split them up randomly into 50 groups. And the first group, selected randomly, all were told to take an aspirin every day for 1 year. And the 50 that were in the other group were told to take a placebo every day for 1 year. So everybody thought they were taking something to control for the placebo effect, but only 50 of them actually had the aspirin every day. And at the end of this, we had a confidence interval. So again, we looked at the mean from our sample of 50 that took an aspirin every day. We looked at the mean from our sample of 50 that did not take an aspirin every day. And we got an interval that was negative 22.15, 2.47. Now the negative means that the non-aspirin group would be more. They had a blood cholesterol of 22.15 more. Their blood cholesterol was more than the aspirin group. And the positive 2.47 tells me that the aspirin group could actually be 2.47 more than the non-aspirin group. So the question says this: does this interval give evidence that there is a difference between the blood cholesterol levels of adults that take an aspirin every day and those that do not take an aspirin every day? And the answer here is no. Why? Because zero's in the interval. Look at this interval again, guys. The negative tells me that the non-aspirin could have a higher blood cholesterol level, or the positive number tells me that the aspirin group could have a higher blood cholesterol group. So the aspirin group could be higher or lower. The non-aspirin group could be higher or lower. And you know what other number, a very important number, is inside that interval? Zero. Zero's in that interval, which means that the answer, is there a difference, could actually be no. There could be no difference. Remember, zero would mean that there's no difference. Zero would mean that the mean for the aspirin group is equal to the mean for the non-aspirin group. So in that case, that there would be no difference. So does this interval give evidence of a difference? No, it doesn't. this interval actually tells me that taking an aspirin every day is not a guarantee to lowering your blood cholesterol. Because again, our confidence interval did have a positive side to it. Now, it doesn't matter that the positive side was smaller than the negative side. That doesn't matter. The fact remains that the true value could be positive, which means that if you take an aspirin every day, you might have higher blood cholesterol levels. So who knows, right? And that's the whole point here. We would rather see an entirely negative interval. If the entire interval was negative, that would tell us that the group that did not take an aspirin, on average, is higher than the group that did take an aspirin. But again, that's not what we saw. So the question says, does this interval give evidence of a difference? No, it does not. 0 falls in that interval, which means that there could be no difference between taking an aspirin every day and not taking aspirin every day and trying to lower your blood cholesterol levels. So again, we could actually use these intervals to help us justify a claim and find some evidence. So if somebody says there is a difference, I would say, hold on a second. I don't think my interval justifies your claim. If I go back to this problem and somebody says, athletes do spend more time per night on their homework, I would say, yes, this interval does justify your claim. There is evidence that that is true. So make sure that you read the question. But you know what? You first got to be able to truly understand what that interval is telling you. That way you could properly give the right answer of yes or no. All right, guys, that's it. See you in the next video.